Um, I'll start off by just explaining what this work is about, and mostly explaining what the title means, so the quantum supremacy Tsirelson inequality. To give some context for this work, arguably the single most important inequality in all of quantum information is the Bell inequality. And the reason why the Bell inequality is so important is that it makes an experimental prediction about classical mechanics that can be violated by quantum mechanics. In particular, it says that there's this game called the CHSH game involving a referee and two non-communicating players, such that using any strategy that is explained by classical mechanics, essentially, the probability that these players win this game is at most 3/4, or 75%. And hence, if you're able to demonstrate in a physical experiment that you can play this game and win with probability 76% or 75.1%, just anything above this threshold, then somehow you've inherently revealed something non-classical about the universe. And indeed, we know actually if the two players share entanglement, actually they can do slightly better than 3/4. In fact, if they share a single EPR pair, they can actually win with probability cosine squared pi over 8, which is about 85%, and that's higher than 75%, of course. And this has been experimentally demonstrated. But this also raises an extremely natural question, which is, what is essentially the quantum upper bound for this game? So classically, using classical strategies, it's 3/4. And this brings us to what's arguably the second most important inequality in all of quantum information, which is Tsirelson's inequality. And Tsirelson's inequality says that actually using quantum strategies, this cosine squared pi over 8 is actually optimal, which if you think about it, is actually kind of remarkable, right? We don't live in a world where you can get all the way up to 1. It's this weird intermediate world where you only get up to cosine squared pi over 8. And besides being just a natural question to ask, we also know in hindsight that actually this was a really good question to ask because it led to what is essentially the modern study of quantum non-local correlations and quantum non-local games that essentially culminated in some very recent wonderful results, like showing MIP star equals RE and refuting the Kahn embedding conjecture in operator algebras. So this is certainly a good question to ask. So why am I opening with talking about quantum non-local games in a talk about quantum supremacy? Well, what I'm going to argue next is that something very similar is going on in the world of quantum supremacy. Recently, as in just a little over a year ago, a team based at Google announced the first experimental demonstration of quantum supremacy on a physical device. And they did it for a task called random circuit sampling. So they would choose a random quantum circuit C on n qubits with random 1 and 2 qubit gates, which I've stylized here. And the benchmark, okay, so the task is to sample from this circuit's output distribution. And the benchmark they used is the so-called linear cross-entropy heavy output generation task, which I'll abbreviate as XHOG. And the task is to just output a string Z such that this quantity is large. And this quantity here, you'll notice this is just essentially the probability that you would measure C if you were to actually sample from the true output distribution of this circuit. And the reason why we use this task is that intuitively, this shows you that the outputs tend to concentrate where they should, basically where these output probabilities actually are large. And so why was Google able to claim quantum supremacy? Well, the reason is that Aaronson and Gunn, also just a little bit over a year ago, proved what is essentially a computational analog of the Bell inequality for quantum supremacy. And what they showed is that under a plausible complexity theoretic conjecture, any classical polynomial-time algorithm for spoofing this XHOG benchmark cannot do much better than essentially random guessing. So this 1 over 2 to the n on this benchmark is what you get if you just guess C randomly, because there's 2 to the n possible strings, and this forms a probability distribution, so they have to average out to 1 over 2 to the n. And Aaronson and Gunn show that with an efficient classical computer, you cannot do substantially better than that, probably. And hence, when Google announced that they are able to achieve an XHOG score of 1.002 over 2 to the n for n equals 53 qubits, this is essentially enough for them to claim quantum supremacy. But just like in the last slide, this raises the very natural question of, well, what's the best that a quantum computer could do on this? And that's sort of what we focus on in this work. So what value of b for b over 2 to the n can you achieve using, let's say we had like a fault tolerant, so even like a perfect quantum computer constrained to be polynomial time. And interestingly, just like on the previous slide, there is sort of, just like on for the CHSH game, there's the trivial upper bound of 1 on the probability that you win. So here, this sort of is like an information theoretic upper bound. One can show that as long as this circuit architecture is like sufficiently random, you get something that's like order n over 2 to the n as the largest possible. On the other hand, sort of the best algorithm we know is to just sample directly from C. And again, assuming the architectures that you use is like sufficiently random, one can show that this achieves something on the order of like 2 over 2 to the n. And so there's just this gap here where we're asking, what's the best you can do on with an efficient quantum algorithm? And I should give a shout out also to my advisor, Scott Aaronson, who was sort of the first person to present this problem to me and also suggest this nice analogy with the quantum non-local games. And oh yeah, of course, I suppose I should also mention, so the reason, of course, why Google did not achieve 2 over 2 to the n is because they used a noisy device. So with that noise, you certainly can't hope to do this perfectly, but because it was bounded away from 1 over 2 to the n, that was enough to claim supremacy. So I'm going to move on and talk about essentially the main result of this work. And for a main result, we essentially studied this question in the simplest non-trivial model in which we can say anything interesting about this question, which is to say we study this problem in the query complexity model. And that means we suppose that the circuit C, we'll model it as just like a Haar-random unitary, and we'll say you only get to make black box queries to C. So you don't get an explicit description, you just get to make queries. And then the question is, how many queries to C do you need to beat this naive algorithm? And what we show is that actually an exponential number of queries are needed to do non-negligibly better than this 2 over 2 to the n, assuming you have a Haar-random n-qubit unitary. So I'll just give you some time to sort of parse this, but I'll also mention that we have some similar results for other oracles. So in some cases, you can sort of replace this by certain classical random oracles plus some quantum gates. And I'll also mention that we can show that this is tight up to this constant in the exponent, as there is an algorithm that achieves this using something like 2 to the n over 3 quantum queries. And this is essentially just a slight generalization of the quantum collision finding algorithm of Poissard, Fourier, and Tau. So this is our main results.
So sorry to interrupt you, William.
Yes.
So there's a question from Maris Ozos, and so he wants to clarify about the expectation. So is the expectation over circuits? So that's
yes, that's a good point. So it's both over the output distribution of the algorithm and over the input to the problem, over the choice of the circuit C. Thank you. Yeah, that's a good question. Okay, so why is this interesting, I guess? Well, I'll say a little more about this. So I think there's a few reasons to care about this result. The simplest one being that it's a real world problem, right? If you care about quantum query complexity lower bound, certainly you should.
Okay, sorry, William, to interrupt you again. So there's another clarification that from Pierre Emmanuel, and so the question is, why we are interested in the deviation from 2?
Again, so the reason
So
why
just from the previous slide.
So 2 over 2 to the n is sort of what the naive quantum algorithm achieves. That's what you get by just sampling directly from the circuit. So yeah, I guess what I'm saying is sort of before this work, this was the only algorithm that was known.
Okay, and so and yet another question. Okay, so how does the complexity scales with epsilon?
Oh, it's something polynomial in epsilon. It might be like epsilon to the 5/4. I don't remember exactly. Yeah,
Okay,
it's something weird.
Okay, thank you.
Yeah. Okay, good. So yeah, it's a real world problem. That's one reason to care about it. I think another reason to care about this is that this problem really differs a lot from other query complexity problems in 2 ways. One is that it involves these random unitary oracles, right? Normally in query complexity, we usually think about Boolean oracles. So you make queries to some n-bit string and you get back like 1-bit answers. But here you're literally querying a Haar-random unitary. And another thing is that it's not—
Sorry, one more question.
Yeah.
Sorry, William. And so that's exactly from Arute does exactly about the queries. What does it mean to query C? Okay, thank you.
Good. It just means you get to apply C. So C is a unitary transformation. You get to apply C. I guess this could be contrasted with you get to like query the entries of C, if that's what you're thinking about. So it's not that. It's just you get to apply C as a black box.
Okay, and yet another question. Sorry. So would C be a T design? Would be better than a random Haar measure?
What do you mean by better? So I might address this later. Maybe
Well,
I'll defer that. I'll defer that to the end. Yeah.
Okay.
Okay. So yeah, so it's not a decision problem. And basically as a result of this, not involving random oracles and not being a decision problem, we kind of need some new tools to be able to solve this. So there are off-the-shelf tools and quantum query complexity lower bounds, namely the adversary method and the polynomial method, but they sort of both have limitations for these problems. So the adversary method is only known to tightly characterize the quantum query complexity of decision problems, and it's not at all clear whether you can apply it here. In principle, it turns out one actually could apply the polynomial method here, but the fact that it involves these random unitary oracles is also just very different than anything we normally deal with these Boolean oracles. And so I would say, at least conceptually, some new ideas are needed. And I'll, for the rest of this talk, I'm basically just going to say a little bit about some of the ideas that went into this lower bound. And I'll start with what I think is maybe the single lemma that might be the most likely to be applicable elsewhere, and it's something about state preparation oracles. So oftentimes in quantum algorithms, we want to consider quantum algorithms that have access to a state, some n-qubit state psi. And so how can we do this? Well, we could just give the algorithm psi, or more generally, you could give it copies of psi. But really, maybe what we'd like to do is say, okay, we'd like to give the algorithm the ability to produce as many copies of psi as it wants. So why don't we give it an oracle that allows it to produce copies of psi? And kind of the most common way we do this is by what I like to call the canonical state preparation oracle. And this is an oracle U that acts as follows. So we fix some canonical state bot, which is orthogonal to psi. You can think of this as being like the all zeros input or something, just some fixed input. And U will swap bot and psi. And then on everything that's orthogonal to these two states, U will just act as the identity. And this lets you produce copies of psi because you just feed in bot and you get one copy of psi. And it's also, like, the reason I call this the canonical oracle is that it's in some sense the simplest oracle that has this property of letting you produce copies of psi. And in certain cases, it can also be shown to just follow in a black box way from essentially any other oracle that lets you produce psi coherently. So that's one model of state preparation oracles. But another model of state preparation oracles that turns out to be very natural for our purposes is what I like to call a random state preparation oracle. And this is a unitary transformation that acts as follows. So you're promised that it has psi in the first column. And that basically just means that on the all zeros input, you get a copy of psi when you apply V. And otherwise, everything else on the subspace orthogonal to psi, this unitary transformation just acts as a Haar-random matrix. So it's just completely random, all the other entries. And you can ask, what is, well, okay, a priori, right, these two resources look very different. But actually, what's interesting is that we show that actually in the query complexity world, these two resources are essentially equivalent in the sense that given query access to one, you can simulate query access to the other using a constant number of queries up to exponential precision. I should note that there is like a subtlety here, which is that this is really a unique oracle. This is really actually a distribution over oracles. So you do have to be a little bit careful about what this means. But if there's any questions about that, I'll defer that to later. And you could imagine maybe some lemma like this being useful for like cryptographic protocols or something. So I thought this was interesting. And the reason this turns out to be useful is that whereas this is the oracle we have, this Haar-random oracle, this canonical oracle is like conceptually much easier to deal with. And indeed, we actually have some lower bound tools. There's a theorem of Ambayanis, Rosmanius, and Unruh in 2014, which says that if you have queries to this canonical state preparation oracle, you can actually approximately simulate any algorithm that queries this oracle using some special resource state. And all this is a bunch of copies of psi plus in superposition with something else. And the number of copies of psi you need is something like the square of the number of queries you make. So by appealing to this lemma, we can say we can just replace queries to the oracle by copies or by some resource state. And in fact, it turns out that for this specific problem, in fact, you can even reduce this just to k copies of psi. So t queries can be simulated by like t copies of this unknown state. And from there, we can actually get a nice lower bound, again, sort of using the symmetries of the problem. Yeah, I don't know if I have time to say any more about that. So I think I'll maybe just move on to the last slide, where I'll talk a little bit about some of my favorite open problems. So the most obvious open problem is to just improve the bounds between the lower and upper bounds we have. And if I had to guess, I would actually guess that this 2 to the n over 3 is more likely to be tight. And that's just that the intuition for the lower bound is that it somehow involves collision finding no matter how you look at it. And that sort of suggests that probably the naive collision finding algorithm is optimal. At least that's my intuition. But I could be totally wrong. And it would, I do talk a little bit in the paper, some ideas for how you might improve this, but I think it would probably need a pretty different approach. I think the other obvious question is to give more evidence that this problem is hard in the real world. So again, we show a query complexity lower bound, but in some sense, while I did argue that this is interesting, it somehow said very little about the actual problem we were interested in, which is, if I give you an explicit circuit, how hard is it to produce this output? Can you relate it to like the hardness of some sharp P problem, for instance? That's essentially what Aaronson and Gunn did for like the classical Bell inequality analog of what I proved. But they rely on an assumption that is, as far as I know, is just not true for quantum computers. And it's not clear at all whether any argument along the lines of what they did could tell you anything interesting about the quantum hardness of this problem. So that's another interesting question. I think the last interesting question is just to also try to understand more about these, the behavior of these random quantum circuits. So sort of implicit in this argument, and this actually, so this is where I was getting back to this question someone had about unitary designs. So implicit throughout this work is sort of an assumption that when you, in this query model, when you have queries to a Haar-random unitary versus queries to a random quantum circuit, that these are essentially computationally indistinguishable. And I think it would be interesting to try to give more evidence of this, or whether this is true or false. And we know that random quantum circuits sort of information theoretically approximate the Haar measure, which is to say that they are, in fact, T designs for some T. But I think to me, it seems quite plausible that actually, like computationally, maybe even with exponential resources, it should be hard to distinguish random quantum circuits from the Haar measure, at least if you're only given quantum queries. So I think that's about everything I wanted to say. I'm happy to open it up to questions, and I guess I still have a couple minutes. So if there's no questions, I could also just go back and say a few more words.
Yeah, you do have 3 more minutes, so you can talk more. Sure.
Okay. Yeah, maybe I'll say just a little bit more about the proof here. So again, I basically argued that we can reduce this problem entirely to supposing, well, essentially what we show is that the task reduces to the following. If I give you a bunch of copies of some quantum state psi, what is the best strategy for outputting some n-bit string such that the amplitude of psi on that n-bit string is as large as possible? And what we argue is essentially that the best strategy for this is just to measure all of the copies of psi in the computational basis and then output whichever string appears most often. And then this turns out to sort of involve some sort of like collision problem, birthday collisions essentially. But I don't think I have time to go into more detail about this. That's just a very, very high level, some of the ideas.
Okay, thank you very much, William, for your very interesting talk. Okay, so let's start with the questions. And so the first question from Omar Fauzi is, where does the depth of the circuit come in?
Good question. So in some sense, that's not really addressed in this work. Or rather, that comes in this last part, which is when do, at what depth do random quantum circuits become like computationally pseudo-random? And I don't necessarily have an answer to that. But I think that's an interesting question.
Okay, so another question from myself. Finally, so you were talking about the tight bound. So we know that you can prove the collision over bound using the polynomial method. So is it possible to somehow combine your over bound with the polynomial method and like prove that to the n over 3 is the correct over bound?
Yeah, so actually that's essentially how I conjecture that you could do it. So for one of the other results in our paper, which I sort of didn't touch on, we actually do use the polynomial method. So you actually can use the polynomial method for these types of lower bounds. And it would not actually surprise me that much if you could use the polynomial method here as well. So yeah, maybe that's possible.
Okay. Yeah, so there are no more questions. So please ask your questions fast. We have only 5 more minutes for the next talk. Okay, and Yeah, otherwise we're just waiting for more questions.
I mean, I guess if there are no more questions, we can also take them offline or take them.
Question.
Okay.
I think one question is going. Maybe I think that someone was typing in the Slack. So let's wait for 1 more minute, and then we can go for the next talk.